So far we've looked at, if we have one continuous outcome, how we can compare this between groups. And first we looked at two groups and then we looked at more than two groups. Now we're going to look at how we can compare one continuous variable with another. Oh, there I am. And we would do this to have a look for associations, relationships, and in some cases make predictions. I've got up there an example that we saw back in week 2, looking at the relationship between household firearm ownership and firearm deaths, and this would be a common way that we display this type of data with a scatter plot, often with a line through the middle if there is a strong relationship that we want to show. I've got another example here. This one is between drinking years, which would technically be a count variable, but it looks continuous enough that we can treat it that way, and the relationship with diastolic blood pressure. And in this case we're actually showing three variables because they have looked at the drinking years, diastolic blood pressure, and also race, and then they've split that up over two graphs for men and women. So the simplest way to fit a line to data points is to fit a straight line, and we call this simple linear regression just because it is the simplest form of regression. Not everyone finds it simple to do, and we're going to use this only if a straight line fits really well. If a straight line is not a good fit, then we probably need to fit a curve or fit something a little bit more complicated. The process is very similar and reporting the results is very similar, but we're not going to go through any of the mechanics in this class. So all we're concerned with at the moment is just looking for, is a straight line a good fit or is it not? We still want to check on the outliers because they can have a pull on the line, and this is in a very similar way that they can have a pull on the mean. And again, it's like a seesaw, that if you jump on the middle of a seesaw you have much less effect than if you jump on the end of a seesaw. And I found a beautiful illustration of this. So if someone who was an outlier, let's say they were very heavy, was going to jump on this seesaw and they jumped up on the end here, that would send a lot of people flying. But if they jumped on the middle over near this guy, oh no, sorry, this guy, then they would have very little effect at all. So when we're looking at outliers, we're looking to see whereabouts on the line are they hopping on, because that will make a difference as to how much pull they have on the line. We also still look at variation, and what we're technically checking for is the variation homoscedastic, homo meaning the same and hetero meaning different, and what we're looking for is the variation similar across the whole regression line. So we want to find something that looks like this graph here. Typically what we'll find, and it's not something that you can easily fix, is we often get this kind of pattern here, and this just happens commonly because there's less room for movement at the lower end of a scale than there is at the upper end. So an example might be if you were looking, say, at car prices, down at the cheap end of cars they might all be fairly similar, say between $1,000 and $5,000. I don't know. So cheap cars might be all similar, but the variation might be huge when we get up to the expensive range, perhaps going from $50,000 up to, who knows, $1 million or more. We also still check for normality, but as the analysis gets more complicated, it becomes something which is difficult to fit at the start of the analysis, and we actually check it at the end. And this is called a residual analysis. So what's going on with this is we're trying to fit a straight line through the data points. Wherever that line crosses closest to the data point is called the fitted line, and this might be our predicted value if we were going to predict something. And usually it's not exactly the same as the actual data line, so there's a bit of error involved whenever we're fitting a line, and this is called the residual. Sometimes it's very small, sometimes it's very big, and what we're assuming with simple linear regression is that all these errors, if we graph these separately, will look approximately random and normal. And we're not going to go in depth into this, but you should have an understanding that there are some extra steps in checking a model when we're using these. So this would be an example of what we might do with our residuals. We might do one plot to check, do they look random? And then we might do a histogram to see if they look normal. Now we're also interested in the strength of the relationship. Previously we would have looked at correlation, and this is often written with a little lowercase r. Correlation goes from 1 to -1. So 1 is perfect correlation, 0 is no correlation, and -1 is perfect negative correlation, meaning that as one variable goes up, the other variable goes down, but it's still a very tight relationship. R squared is, in its simplest form, just the correlation squared, and how we interpret this is that it's how much variation in the data can we explain with our regression line. Now because we're squaring it, R squared values are always positive. If there's no relationship, if there's no correlation, then the R squared will also be very low. It means we can't explain very much of the variation in the data with our line, and that would be close to 0. If you had perfect correlation near 1, then you would get a very high R squared. Same with perfect negative correlation, you would get a very high R squared, meaning that you can explain a lot of the variation in the data with your regression line. And I found this cartoon and I think it's really funny, so hopefully you all agree with me that that's just hilarious. Now just because two variables are correlated, of course, doesn't actually mean that one causes the other. And we have no statistical test for nonsense, even though that would be really wonderful if we did. So we do have to think about the variables and think, is this a genuine relationship, or is this what we call spurious? Is it just due to chance? Is it just random and it just happened? If we want to say that one variable causes another, then ideally we would have some kind of experiment or randomized controlled trial. There are other ways to look for causation, such with a dose-response relationship, or building up a lot of evidence through good observational studies, perhaps cohort studies, over a period of time, as was done with smoking. And I've put some examples in of nonsense, just so that you get a bit of practice at looking for it. So there is a very strong correlation between per capita cheese consumption in the US and the number of people who died by becoming tangled in their bed sheets. And there's a few more there for your enjoyment, and the website's linked in the notes. So you can have a look through those, and hopefully you'll see that if you trawl through enough data, eventually you'll find correlations between two things, but that doesn't necessarily mean they're actually linked. So an overview of simple linear regression. This is a little example about how many days downtime do you need between games and the age of the player. So the outcome here is downtime, and the predictor here is age. So we can look at the relationship with a scatter plot. We can fit a line through the middle. The difference between the line and the actual point in each case is called the residual or the error. The common form for the equation is the y equals mx plus c that you saw in maths class in high school. And this is often written with y's and x's, and whenever you see little dashes on top of the y's, that means they're predicting something. If we put the variables into the equation, we can read this out as saying downtime is predicted by these numbers here and some multiple of age. And the things that we want to think about is a straight line a good choice, or does it need to be a curve or something more complicated? Do any of the data points seem to be having a very strong pull on the regression line? Are all the errors random and normal? And how much of the variation in downtime can we actually explain by age? If we extend beyond simple regression, we can add more variables into the model or more complex patterns. When we try to use an equation to describe data, this is called modeling, and the model refers to all the variables which are in the equation. If you see something with a squared or a cubed in it, then it means there was some kind of curve, and sometimes again more complicated patterns. So key terms for understanding the research: when a researcher says they fit a model, that means they're talking about the variables they've used to try and explain something. The coefficients are the numbers that we would need to actually write out the equations, and these are often called lowercase b, capital B, or the Greek letter beta. You'll see a few variations of that depending on the software. And again, the R squared is how much variation in the data is explained by the model, where 100% means a perfect relationship, and we could theoretically predict one variable based on another with no error. Now, obviously, in any studies based on people to do with health, you would never get 100% correlation because people are just not that predictable. Here's an example table where they have fit a model to a particular outcome. So they're trying to predict self-rated health score in the elderly. They haven't just fit one model, they've tried to fit 4 models, so they're looking to see which combination of variables might be a good predictor of self-rated health. If I grab my little pointer here, we can see for model 1, they've included these variables here down to health insurance, and then they've given the R squared. So how much variation in self-rated health can be explained by this particular set of variables. Then for the next model, they've tried adding a few more health behaviour variables in, and there's the adjusted R squared down here. It's gone up a little bit. Then they've added a few more variables in for health status, and again the R squared has gone up a bit, meaning we're explaining more variation in the outcome now. And then the final model, which has got a ton of variables in it, is explaining even more variation in the data. But you'll notice that it's still not that high. So they've got up to 35%, and that's, considering it's on health, this is actually quite high. So they're explaining 35% of the variation in self-rated health scores in the elderly with all of these variables here. So that would be a fairly typical output. And then what they've done is any variable which was significant, they've put a little asterisk by. And this one way to do it. Often you actually drop variables if they're not significant, but that would be a topic for another day, another course. So real data is usually very messy. I really like having graphs where possible, but sometimes the trend is so tiny you can't see it, and we do have to be a little bit skeptical here sometimes if the trend is really, really tiny. If there's no graph, it could also mean that the relationship is just very complicated and it needs a lot of variables, and so it's not possible to put it all on the same graph, such as with the previous example. And the interpretation obviously always depends on context. Is there a benefit at the epidemiological or the public health level if it's a really tiny effect? Is there enough of an impact that it's something that you would recommend one-on-one in sort of a clinical situation? When we're trying to interpret how strong or how good a relationship is, it's quite handy to put a confidence interval on a graph. If you see a graph that's got these shaded areas or perhaps 2 curvy lines each side, then that would be an indication that they fit a confidence interval to their regression equation. The confidence interval will usually be narrower in the middle of the line, and that's because we're more sure there because we've got more data, and then we're a little bit less sure as we get out to the outside of the ends of the regression line. This particular example was from a blogger who wanted to look at his step counts in relationship to the weather, and he wanted to know, did he actually do take more steps if the weather was good? And so what he's got along here is his step count. You can click through that link if it's too small to see there. And the temperature on the x-axis, and then his step count on the y-axis. The null hypothesis is that there's no relationship between temperature and step count, and his p-value was 0.096, so no evidence to reject the null hypothesis or no evidence of a relationship. If there is no relationship, then that's equivalent to fitting a flat or horizontal line through the data. And indeed, if you have a look at the shaded area of the confidence interval for the regression line, you can probably see that you could fit a flat line through that shaded area. What if we want to control for another variable or for lots more variables? It's actually quite simple, and the software will do all the maths for you. Difficult to graph more than 3 variables together. So in this case, he's wanted to control for whether it was a weekday or the weekend, because obviously we have different behaviours whether we're at work or not. And so on average, you can see that there were fewer steps on the weekends, but it does look like there's more of a trend. So as the temperature rises, it looks like his step count is actually increasing, and I believe this particular relationship was significant, but then there doesn't actually look like there's much of a difference at the higher temperatures. I'm not going to interpret this as a scientific study because this is just one guy taking his own data. If the relationship with a variable changes depending on another variable, then we call this interaction or sometimes moderation. So if the effect of temperature on your step count is moderated by whether or not it's the weekday or the weekend, then we would call this an interaction effect. And this type of analysis might be called ANCOVA, multiple regression or general linear model. So sometimes two-way ANOVA with interaction. Gets a whole lot of names. Anything with ANOVA, regression or model, linear model, is probably falling under this family. It's a great big family of techniques. So if you want to understand more about interaction, you can probably think of it the same way as we think about drug interactions. And I found this nice little interaction checker on the fabulous interwebs. Here you can type in 2 drugs and see if one drug changes the effect of the other drug. And someone happened to mention this in a tutorial, so I thought I would look up caffeine and vitamin B1. And apparently your absorption of vitamin B1 is reduced or moderated by caffeine intake. And so this would be called a drug interaction, and statistically we would call this an interaction too.